Okay. So thermal energy and heat. Let's start off talking about thermal energy. And before we do, you know that what we talked about so far in terms of total mechanical energy has involved kinetic energy and gravitational potential energy. Now, having said that, when you take something up high, you give it gravitational potential energy. Do you make it hotter by taking it up high, though?
Yeah.
I don't think so. No. I mean, really, the idea is no. And you know what Joule, the guy who the energy is named after, the energy unit is named after, what he did, and he actually did this on his honeymoon, according to legend. He actually went and he took measurements with a thermometer at the top of a waterfall, and then made his poor new wife go to the bottom of the waterfall with him. Yeah, exactly, right? There must be better ways to spend your honeymoon. And he actually took the thermometer at the top and at the bottom and checked to see if it was hotter at the bottom than at the top. And here was his thought. He thought that maybe, just maybe, the gravitational potential energy at the top would get converted to kinetic energy. And as we all know, kinetic energy has to do with particles moving around with speed, right? And so he figured, okay, so whatever water molecules get down to the bottom is going to have more kinetic energy, so they're going to be bouncing off in all directions with greater speed, so then they'll be hotter. What do you think he found?
Nothing.
No, there's no appreciable difference. He'd measured no difference at all. No thermal energy change from the top to the bottom. But he wasn't totally off. The idea of thermal energy does have to do with kinetic energy. Okay, so thermal energy is the total kinetic energy and potential energy of atoms or molecules, well, I guess atoms and molecules, in a substance. In other words, if you could zoom right in on a substance and you could look at all of its molecules or atoms or whatever particles it's made out of, and you could measure the speed of each of those particles, and you could also know the mass of each of those particles using maybe some knowledge from chemistry, then you could add up all the kinetic energy, 1/2 mv squared, and that would be heat energy. Problem is, not very practical. Why not?
Counting molecules is very difficult.
Yep.
Time-consuming.
Time-consuming to count molecules. Yeah, and what about the speed issue?
But yeah, they're also moving incredibly fast. Or not at all.
Yeah, they're moving pretty fast, some of them. So you got to get in there with a speed radar gun like the cops and shine your speed radar gun at each individual molecule while you're counting them. That's not really practical. I mean, really, at the end of the day, although we are theoretical thinkers, we got to think about what's realistic, okay? And that's not really very realistic. So here's another idea that people are talking about. Another idea that people are talking about is temperature. Temperature. And while thermal energy might be the total kinetic energy, temperature, what people say, is a measure of the average kinetic energy of the atoms in a substance. I'll just say particles. Okay? So if I were to look at a cluster of particles, let's just choose 3 to be simple, and I said that one was going that fast, and one was going that fast, and one was going that fast. Well, the average speed of those 3 particles might be well, somewhere in between, maybe as long as the middle length arrow, might be going that fast. And so the kinetic energy of this guy here would be the kinetic energy, would be the temperature for the system. So average. It's the idea of averaging, okay? And that sort of makes sense too, right? So if I take a look at a glass of water, maybe some of the particles are moving very, very quickly. Maybe some of them are moving very, very slowly. And on average, what's the average speed? Well, the average speed is going to tell me something about the temperature. Okay? Something about temperature. If it does have to do with motion, there's actually a few ways to measure temperature. And actually, Celsius is a nice measure. The way that Celsius was developed is there's this fellow named Celsius. Yes, a fellow named Celsius walks into a bar. And he stuck a thermometer into freezing cold water. And he marked off on the thermometer that that was 0. He defined it as 0. And then he found that, well, actually, he didn't just call it a thermometer at that point. He really just was a glass tube with a bottom that had been closed off. What did he fill it with? Mercury. Yeah, he filled it up with mercury. Here I am coloring it in red because I'm so used to these red alcohol-filled thermometers. But the first ones were mercury. Mercury, he found, expanded fairly steadily, like had a fairly regular expansion rate as you put it into different temperatures of things. So mercury was chosen, and he put the mercury into cold water, or freezing cold water, and it got to a certain height. And he had a bunch of different tubes that were roughly the same diameter, and turns out that it went to the same height every time. He said, oh, I'm onto something. Then he put it into boiling hot water, and every single time it went up to the same height. So we call this 100 degrees, 0 degrees, and since he came up with the idea, get to call it Celsius, named after him. And then, just to be fairly consistent and regular about these things, just broke it up into 100 smaller units. Now, why choose 100? Just so you can be pretty accurate. 100 pieces of unit measurement, that's pretty fine. Why not make it 1,000? Well, that was his prerogative, right? Like, he could have made it 1,000 degrees Celsius was the boiling point. It actually is a little bit arbitrary, isn't it? Why choose 100? Just because he said so. And so we're stuck with this 100 as being the maximum. Not the maximum. The maximum point that water gets to before it starts to boil. But 0 to 100, why not make it 0 to 1,000? Celsius choice. Yeah?
So with Fahrenheit, how come it's like 32?
Oh, Fahrenheit's a different measure. That's really more of what we would consider to be an imperial measure, kind of like inches. Kelvin. Yeah, well, that's where I'm going next. This is Celsius measure. Okay? This is Celsius. And that's one basis for measuring temperature. And it's a great way to measure temperature because it's based on water. And the nice thing is that since it's water-based, or the main measurement points are based on water, it relates really well to humanity. It actually relates really well to planet Earth because what's the largest abundance, most abundant solvent we have on our planet and in our bodies? Water, yeah. So water is a really relevant thing to our planet. Might be water. Now, Lord Kelvin said, you know what, Celsius, you got a great idea here. I do like the idea of having little gradations in temperature. However, Kelvin, kind of like Kevin with an L thrown in the middle. Okay? Kelvin, Lord Kelvin. He said, you know what, I like it. I like that you have these little measurement units. I'm not against that. But I think I'd like to go with something a little more universal than water, and recognizing that the motion of particles really is what we're talking about here, let's talk about setting the 0 at a different spot. Let's talk about the 0 being a theoretical value, where 0 Kelvin looks like okay, but we don't call it 0 degrees Kelvin. It's just 0 Kelvin. 0 Kelvin is the point at which the kinetic energy of these particles is equal to 0 joules. In other words, are they moving? No. So, but well, if you actually get the particles to not move anymore, some really crazy things happen. People start talking about superconductors and all this sort of thing. But we're not going down that road right now. No. It's a conductor that allows electrons to go with 0 resistance. Yeah, it is kind of a neat thing. But that's not where we're going right now.
Isn't that absolute 0 at which point would be,
I love it. You are always 2 steps ahead. So what we're saying is that at 0 Kelvin, or where kinetic energy is equal to 0, we call this not just 0 Kelvin, but better yet, we call it absolute 0. Yeah. The point at which particles stop moving around. And maybe some weird things happen at that point. Maybe we get superconductors that are absolutely perfect. Yeah, well, so far we haven't been able to get there. We've been able to get super, super close, but never actually there yet.
What's the degree Celsius for that?
Degrees, oh, thank you. Yeah, we do have a degree Celsius associated with it.
Isn't it negative 270?
Yeah. So 0 Kelvin is equal to negative 273 degrees Celsius. And we could throw in some extra sig figs there. It's actually 273.15 degrees Celsius. Negative 273.15 degrees Celsius. A lot of the times people just write it as negative 273. So that means that when I'm at, that's minus 273, that is cold, man. You better wear your woolly underwear if you're there. So 0 degrees Celsius, hold on. 0 degrees Celsius would be what in Kelvin? 273.15 Kelvin. So it sounds like it's pretty hot in Kelvin, but in degrees Celsius, that's 0. That's freezing. In fact, you go grab yourself an ice cube and say, oh my gosh, oh honey, this is hot. This is a hot ice cube. It's 273.15 Kelvin. Woo! What is it really?
0 Celsius.
Yeah, 0. And actually, you know what? A Kelvin, 1 Kelvin, is the same magnitude as 1 degree Celsius. And what I mean by that is the unit of a Kelvin is the same size as a degree Celsius. So we actually do carry on Celsius's legacy because a Kelvin is the same size as a Celsius.
It just starts at a different point.
Yeah, it just starts at a different point. Okay? So if I say that I'm going to make something hotter by 1 degree Celsius, how many Kelvin have I made it big?
Oh, one Kelvin.
Yeah, 1. Okay? So if I say that I'm going to make it 5 degrees hotter in Celsius, how many hotter am I going to make it in Kelvin? 5. 5. Okay? Yeah?
What is
Centigrade? Another word for Celsius, as far as we're concerned. Yeah? Get centigrade because cent en français, n'est-ce pas? Oh, yeah. 100, right? Yeah. 100 grades. 100 bitsies. Yeah. Yeah.
I remember there being some theoretical risk to trying to make a substance reach absolute 0.
Yeah, people talk, maybe the particles will implode and won't hold up anymore, and maybe some funny things will happen.
I heard something that it was, just spread out and stall mini particles.
Who knows the temperature in space, but I do know they'll never hear you scream.
Isn't it possible